Hello, everyone. In this video, we're going to finish a series of videos on gluconeogenesis, and we're going to see other inputs. We've talked about pyruvate for the most part, and lactate in the case of liver, which also will take you to pyruvate. So let's see a few more and see how that works. All right, so here is how we bypassed pyruvate kinase, and we had to go through oxaloacetate. Well, what if you, but both pyruvate and oxaloacetate, they're actually breakdown products. Not breakdown, but you can get pyruvate and oxaloacetate from amino acids. So this is how it works. They are breakdown products, of amino acids. So let's see how that works. So we looked at the TCA cycle, and we have talked about how many of the intermediates in the TCA cycle are building blocks for amino acids. They're used in amino acid biosynthesis as well. When amino acids are broken down, they also generate, in some cases, TCA cycle intermediates. And they can fit into the TCA cycle at various steps. And when you get them at the oxaloacetate state, then all you have to do is just use Pepsi-K and the malic aspartate saddle, and you get them out, and you bypass pyruvate kinase, and then you generate phosphoryl pyruvate. You can go all the way back to the steps of gluconeogenesis that we discussed. So this is how the various amino acids enter compounds that could be used for gluconeogenesis through the TCA cycle. And some of them we cannot, and those are the green ones, and we'll describe them in a minute. So out of the 20 amino acids, 2 of them we cannot, from 2 of them we cannot make glucose, and we'll see why that is. So the other important thing is that if you bring in amino acids through the TCA cycle, actually they can sort of pay for themselves for the cost with all the NADHs and the ATPs and so on and so forth that you need to make glucose. They can pay for themselves. Why is that? Because, of course, especially glutamine is a very important one. They can generate reducing power and ATP, okay, through the TCA cycle. So the reducing power, we have seen all these steps before. So they are not, I guess, as I said before, they pay for themselves. So it's an excellent source to make glucose. Amino acids are an excellent source to make glucose. So, and there is actually, as we sleep every night, there is some breakdown of protein for this purpose, from our bodies, from our muscle, to make glucose, actually. All right, so we have in animals, as we have seen, we have pyruvate and lactate through pyruvate, and of course the various TCA cycle intermediates, and that's how we make glucose. How about acetyl-CoA? Can we use acetyl-CoA to make glucose? And the answer is no in our case, but some organisms that can bypass, that do the glyoxylate cycle, as I said, and they can use acetyl-CoA to go from 2 carbons, okay, to 4 carbons and generate malate here. Then yes, these guys from acetyl-CoA, they can go from 2 to 4, and then they can generate oxaloacetate, which can be used to generate pyruvate, and then go all phosphoryl pyruvate, sorry, and then go all the way to glucose. But we don't have this option. Okay, we don't do the glyoxylate cycle. So a key feature of the glyoxylate cycle, as we discussed at the time, this is a slide we saw in the TCA cycle, is that you can go from 2 carbons to 4 carbons. And this is extremely useful and important for organisms that do the glyoxylate cycle a lot, like Mycobacterium tuberculosis, because that's how they make their glucose. They can break down fat. In this case, it's fat they get from the host, like the person in the lungs. And from that fat, which when it's broken down into acetyl-CoA units, as we will see in a few lectures, they can actually generate glucose. But we don't have that, all right? So we cannot use acetyl-CoA to make glucose, which means anything that's broken down to acetyl-CoA, like these 2 amino acids, leucine and lysine, which are broken down into eventually to acetyl-CoA, from them we cannot they are not gluconeogenic. They cannot they're not glucogenic. They cannot, we cannot use them as substrates for glucose. So you burn down your fat, you won't make any glucose. You can get energy out of it, right, as we discussed, but not glucose. Now, not all our fat is broken down to acetyl-CoA. Most of it is, because especially the even carbon long fats, the fatty acid chains, if they're even numbered, they will be broken down. So they're broken down in 2 units at a time. So as long as they're divisible by 2, so if they're even, then you get acetyl-CoA and no glucose from that. But sometimes we have odd numbered fatty acid chains, and when you break them down 2 at a time, you end up with 3 at the very end, which is propionyl-CoA. It turns out that propionyl-CoA is compared to succinyl-CoA, which is a TCA cycle intermediate, and then you can go to oxaloacetate and so on and so forth. And from then, from a little bit of fat, then I guess you can make a little bit of glucose. Now, that's not a big deal for us in animals, unless you are a ruminant. The bacteria in the cows and all that, they can actually make a lot of propionyl-CoA, and that's a big source of glucose in ruminants. So, all right. So what we've seen lactate in animals for the most part. They can make. You can get in the liver. You can make pyruvate, and then go all the way up to glucose. Other inputs, glycerol, as it turns out. We have a lot of glycerol, as we will see when you break down fat. You have the triglycerides. It leaves. If you break down fat, you leave the glycerol backbone, and that you can use actually to make dihydroxyacetone phosphate. Glycerol is a 3-carbon. It's not a sugar, but it's a 3-carbon unit. And dihydroxyacetone phosphate then can be used, is a glycolytic intermediate, and you can make glucose. So how does it happen? Why is glycerol not a sugar? All right, just out of a little curiosity, there is no carbonyl group on glycerol, right? So the way to make dihydroxyacetone phosphate from glycerol is first to make it glycerol 3-phosphate. There is a glycerol kinase, which just phosphorylates one of the hydroxyl groups here on the end. And that's happening in the liver, by the way, only as far as I know. And then you dehydrogenate, you generate your carbonyl, and you have dihydroxyacetone phosphate. You have glycerol 3-phosphate dehydrogenase, very simple reaction, and that's how you get it. And then you can go on and make glucose from that. And if you do have the glyoxylate cycle, the glyoxylate shunt, you can, from 2 carbon units, you can go all the way down to acetyl-CoA, and then you can, from there you can get oxaloacetate, and you can bypass it, and you're done. So, by the way, I put ethanol here because this is how yeast does it. Okay, so yeast, when it spits out ethanol, it's 2 carbons. It can bring it back in, and it can use it to make glucose. So it's pretty cool. Anyway, these are all these things on the end here. Then we don't have them. All right, so we cannot. All these 2 carbon units, we cannot use any of this as an input, but we can do lactate and glycerol and all the amino acids, as I discussed earlier. So here we're going to close with this video and with all of gluconeogenesis.